तू कैमरा टर्न कर दे.
So, good afternoon, everyone. Really, I am happy to introduce my PhD supervisor, Professor Dr. Ravindra Kishore Mishra, who is a former professor of Electron Science Department, Berhampur University. So, he has already supervised 18 PhD scholars and completed around 5 sponsored research projects during his career, worth of more than 1 crore rupees. He has organized many national and international workshops and summer schools, winter schools in USA, France, Malaysia, Kolkata, Chandigarh, Kochi, Chennai, Sikkim, Bhubaneswar, and many more. So he has received British Commonwealth Fellowship in 1999, INSA Visiting Fellowship in 1996, and he was chairman of IEEE AP MTT sector Kolkata section during 2012 2013. During this period, the chapter was globally recognized as outstanding chapter for 2012 by the IEEE MTT Society and best chapter for 2013 by the IEEE AP Society. And he has been awarded many awards like Indian National Science Academy Teachers Award 2015, Samant Chandrasekhar Award in 2012 for Engineering and Technology by Odisha Vigyan Academy under Department of Science and Technology, Government of Odisha, Hariom Ashram Sri Hari Vallabh Das Research Endowment Award in 2000, Sir J.C. Bose Award 2000 by IIT India, Outstanding Young Person Award 1998 by Berhampur chapter of OYP, and he has served as the associate editor of International Journal of RF and Microwave uh, RFCAD journal that is under Willy. So he is the reviewer of IEEE AP transaction on AP, MTT, IEEE MWCL, IEEE Access, and many more journals. And he is a life fellow of IT, senior member of IEEE, and life member of IST. And this is a very short biography of sir. And I request Honorable uh, Professor R.K. Mishra sir to continue his speech. Sir, please.
Thank you, Professor Behra, for a nice brief introduction. I am really thrilled to be a part of this workshop, and unfortunately, I could not attend it in person uh, like the previous workshops. But in this manner also, I hope I can do some justice to the workshop, and people will benefit from this lecture, which is, as you suggested, metamaterial and metasurfaces. Meta is common in both these words, and each of these words is a combination of two words. Meta is common. Meta means beyond or after. In Greek, meta means this. Therefore, any material which is beyond the normally occurring material, or any surface which is beyond the normally occurring surface, is the topic of today's discussion. We will restrict it to the domain of electromagnetics only. In other domains also these materials and surfaces exist, but we will restrict it to electromagnetic domain so that it fits into antennas and microwave. Here you see a basic picture from our school days. We have a lens, rays are coming to the lens, and at the lens, they bend in a particular manner depending on the curvature of the lens, and they are focused to a point called the focal. Design of this lens is extremely difficult. Optical engineering is very involved in designing this lens. Design means designing the curvature of the lens, thickness of the lens. These designs are extremely difficult. Now, if we have such a lens, this is how it works that we read in the school days. Now, when we came to college, to particularly engineering side or physics side, we studied propagation of plane waves. So you see on the left hand side we have a plane wave which is incidenting on the lens. Now when it comes to the lens, at the edge of the lens, it travels a smaller path compared to the center of the lens. So when it comes out of the lens, at the edge it will come faster, at the center it will come slower. Therefore, the waveform will bend. Then the Huygens principle, based on the Huygens principle, secondary waveforms will be formed. Their wavefronts will propagate and they will converge to the focal. So this is the second form of explanation why lens focuses. Now this, since this design is extremely difficult, if somehow we can replace this lens with a slab whose design is easier, then it will be much easier and much cheaper option. Now, how to design this slab? If is it possible? First, we'll see which is possible. So the slab has to be made up of a special material. That material, whether it is possible to get a material, and if it is possible, how to design that material. That is what we are going to discuss today. Now, for plane waves, we know the electric field E is of the form A into exponential minus gamma r. Gamma is the propagation constant which we give as alpha minus I beta. Now, beta is the phase constant, alpha is the attenuation constant, and beta is omega root over of mu epsilon. If mu epsilon are positive, then beta is positive real. Therefore, alpha term, exponential minus alpha, is the attenuation term of the wave in the medium, whereas exponential I beta term is the propagation term. Here I am using I, although I am conversant with J, but mostly in physics people use I, and the principles that we are going to discuss are derived from physics. Therefore, I am using I for root over of minus 1. Okay, so exponential I beta is the propagating term. Now suppose beta is imaginary. How beta will be imaginary? If mu is negative or if epsilon is negative, beta will become imaginary. If beta becomes imaginary, then I beta becomes I into I beta, because beta is imaginary. I into I is minus 1. Therefore, this exponential I beta term will be exponential minus beta. So that will be again attenuating. So the electric field will attenuate in that medium where beta is imaginary. Now let us see this factor depends on epsilon and mu, permittivity and permeability. Now let us see the materials in terms of permittivity and permeability. We know permittivity can be negative or positive. Usually the dielectrics that we see, these are positive, or these are positive permittivity, whereas metals, their permittivity at frequency, high frequencies will be negative. Similarly, doped semiconductors, their permittivity is negative. Mu usually we know mostly naturally occurring materials. Mu is one that we take. Magnetic effect is not felt much, except for the ferro group. Now, if you have iron, cobalt, nickel, etc., their mu can be different. It can be more than one or less than one. Next. So now let us divide the mu and epsilon quadrant into four quadrants. So if both in a material where both epsilon and mu are positive, naturally there will be propagation. So those modes are propagating. If either of them is negative, if epsilon r is negative, then we have a evanescent mode. This occurs in plasma, metals, terahertz, doped semiconductor. If mu r is negative, then also you have evanescent mode like ferrites. These are all naturally occurring materials. Now, what happens in the third quadrant? Mu r is negative, epsilon r is negative in the third quadrant. We do not know any material naturally occurring where both these are negative. So, what will happen if both of them are negative? Let us try to analyze that. So, first is whether both can be negative simultaneously. Epsilon r and mu r both simultaneously can be negative. Let us look at the conditions. So, if we look from the physics point of view, is physics prevents it or approves it? Now, prevention, there is no law of physics which prevents it. So, physics from physics point of view, they can be, it is possible to have negative epsilon, negative mu. But approval is conditional. What is the condition? Condition is it should satisfy the generalized entropy condition for dispersive media. Dispersive media means beta is a function of f square, frequency square, not frequency. Because beta is equal to omega root epsilon mu. So omega is beta is a function of frequency. Don't take it that way. It has to be a function of frequency square, which means epsilon and mu have to be both functions of frequency square. So that is the condition. Now, if that exists, both are negative, then what will happen? If both are negative, then root over of mu epsilon is positive, therefore beta is real. If beta is real, then there will be propagation, no problem in propagation. So the mode is propagating mode. Now this mode is also called a left-handed mode, and the materials which support this epsilon negative, mu negative are called left-handed materials or metamaterials. Why metamaterials? That we have understood now, because they do not exist in nature, but it is theoretically possible. Practical we'll see later. Why it is called left-handed we'll see later. Now, if both of them are negative, immediate consequence is the refractive index will become negative. How? Let us see it from the physics point. N square, we know refractive index square is equal to epsilon into mu, which means N is equal to root over of epsilon mu. When we have root over, it can have either positive sign or negative sign. Naturally, from the school days, we know if we take a root over sign, we usually take positive sign. But choosing this sign depends on the physics. Now, here in this case, let us say epsilon is equal to minus epsilon r plus I into epsilon I. Epsilon r is the real part, epsilon I is the imaginary part of epsilon. Similarly, mu is equal to minus mu r plus I mu I. Now this plus I, epsilon I or mu I, this shows that These are showing these are metals, these are materials which show passive responses. They cannot show gain, and in these materials there will be loss. The loss is represented by the imaginary part. Now these are so, as you know, any material, their property is not exhibiting gain automatically. So there has to be causality condition. There has to be cause for gain. Otherwise, if they show gain, then causality will be violated. They always satisfy the causality condition. Now, we have to satisfy always the causality condition, so there should not be gain, there can be loss. Metal can absorb energy, consume energy as heat, or dissipate energy as heat, or any other form of energy. So there can be loss, but there cannot be gain. That violates the causality condition or the energy conservation law. Now epsilon and mu we have so given in this form. So root over of epsilon mu will be minus epsilon r plus I epsilon I into minus mu r plus I mu I to the power half. Now expand that, so you will get epsilon r mu r minus epsilon I mu I minus I into mu r epsilon I plus epsilon r mu I whole to the power half. Epsilon I and mu I, both these loss factors are very small. Since they are very small, their product will be extremely small. So that we can neglect in this. So this will be approximately equal to epsilon r mu r minus I into mu r epsilon I plus epsilon r mu I. Now what we will do is we will take epsilon r mu r outside the bracket. So root epsilon mu is equal to plus minus root over of epsilon r mu r into 1 minus I into mu r epsilon I plus epsilon r mu I divided by 2 times epsilon r mu r. Now where from these 2 in the denominator come? Because we have made a binomial expansion of the square root. And so that 2 comes. Now we have to choose the sign, proper sign. This proper sign, choosing the proper sign will depend on what are the values of mu r epsilon r. Those will be valid for all values of mu r epsilon r. Therefore, let us choose mu r epsilon r to be 1. That is one of the values. If it is satisfied for 1, it will be satisfied for all other values. If we choose that to be 1, so this right side will now become plus minus square root of 1, which is 1, then whole into 1 minus I into epsilon I plus mu I by 2. Now this side, and now if I take plus sign, then it will be first part is plus 1, no problem. Second part is minus epsilon I plus mu I by 2. Minus means it is no more causal. It is showing gain. So the material is showing gain. Material with root over of epsilon mu. If epsilon is passive, mu is passive, material with epsilon is passive, mu is passive, then the total material has to be passive. So it cannot show gain. Therefore, it cannot be negative. The imaginary part cannot be negative. Imaginary part has to be positive, so we have to take the negative sign. So positive root means material with gain, that is not acceptable. Negative root shows material with loss, that is acceptable. Therefore, we have to choose the negative sign. So n is equal to minus root over of epsilon mu if epsilon and mu both are less than 0. Now these are called negative refractive index material. Let us see a short historical background. Schuster, in a book in 1904, first proposed this. He tried to see if there can be negative refractive index and what will happen there. Small discussion was there. Then Lamb, Pocklington, Maluginates, Sivukin, and General, they at different times they have also uh, thought of this. Finally, Victor Vasilenko in Russia, he found out the electrodynamics of substances which are showing negative refractive index in 1967. But those all these were theoretical till Pendry, Sir J.B. Pendry in UK, he realized this in 2000. Both negative, mu negative, epsilon negative, he realized. Next. Now definition is a left-handed metamaterial, LHM. These are composed of materials with effective electric permittivity epsilon and magnetic permeability mu. Both are negative over a common frequency band. Next. Now, if that happens, what is changing electrodynamically? So, in electrodynamics, what changes? In electrodynamics, there is no change to the wave equation if the wave is propagating in right-handed medium or left-handed medium. There is no change. It remains omega square epsilon mu E is equal to k square E. That remains as it is. That proof you can see by taking a plane monochromatic wave. When you take that, delta is equivalent to minus ik. Put that in the Maxwell's equations and you can see the proof. Next. This proof I am not going to discuss the algebra. If you want, you can see the my YouTube link which is given at the bottom of this page. There I have discussed it in detail. Then the next part is the Poynting vector. S, Poynting vector, many books put it as P, but some people put P as power, so we'll take it as S. So S is equal to, by definition, E cross H. Now E cross H we can write as E cross K cross E. From where we get this? This is because delta we are using as Ik. So from that, find out the value for H, put that. So this gives you minus 1 by omega mu E cross K cross E. Then use the vector rule, the vector triple product. So that is minus 1 by omega mu K E dot E minus E K dot E. Now K and E are orthogonal to each other, so the second term goes. So we will have minus 1 by omega mu K E dot E. So that we can write as minus 1 by omega mu K E dot E into K by vector K. So that gives you K by magnitude of K. So that K by magnitude of K means unit vector in the K direction. So that we are also writing as minus root over of epsilon by mu into E dot E K by K. So if you look at this, then that shows that S and K, S is on the left hand side, S vector, Poynting vector, and K is the wave vector which is on the right hand side. They are of opposite sign, means they are of opposite direction. So K will be in opposite direction to S. So Poynting vector and wave vector, these are in opposite direction. Since these are in opposite direction, in the negative medium, DNG medium, so the we call it a left-handed medium. Why, that we will see now. Next. So DPS medium, in which both are positive, double positive medium, their E and H are in one plane, and S and K are in the same direction. And if you use the right hand thumb rule, so E to H will be in the plane is in your fingers and thumb is in the direction of S and K. So this follows the right hand thumb rule, therefore it is called right-handed medium. DNG medium, S and K are in opposite direction. Next. So it for the K, it follows the left-hand thumb rule. Therefore, it is called the left-handed medium. In the left-handed medium, energy flow and group velocity, these are in the direction of the Poynting vector, whereas K, which is the wave velocity, which gives you the wave velocity, it is in the opposite direction to the energy flow and group velocity. Next. And now the next term is group velocity. What happens to the group velocity? Vp into Vg, is C square. But in DNG media, Vp into Vg is less than 0. That is the effect on the group velocity. This you can derive from these two formulas. S expression we have seen, and U is the energy density. So that formula, 1 by 4 dou by dou omega of omega epsilon into E absolute square plus dou by dou omega mu with H absolute square. That is the energy definition. Using that, you can find out this. This also you can see the link that I have provided. I am not going to discuss the algebra here. You just see that link. You will find out the expression for Vg and find out Vp into Vg is less than 0. Next. Then comes the Snell's law. N is negative, mu negative, epsilon negative. So N is negative. Next. So N is negative. NRH means in the right-handed media the N. So that is positive. That into sine theta I is equal to NLH. NLH is in the left-handed media. That into sine theta t. Theta t is the transmitted angle. So that will be NLH, we can write that is negative. So that is minus 1 into absolute of NLH. So that we can write in this manner. So from this, we can find out what is theta t. Theta t is minus sine inverse of NRH by absolute NLH into sine theta I. So this will be, since NRH is positive, NLH is positive, and sine theta I is positive. So this will be theta t will be minus sine inverse of a positive number, which is sine inverse of a negative number. So that negative number is, so therefore theta t will be negative. So theta t is less than 0 or theta t is negative. The theta t motion is in the clockwise direction. So you can see in this figure theta I and theta t. Theta I is in the anti-clockwise direction, so that is positive, whereas theta t is in the clockwise direction, so it is negative. Next. Now, what is the magic of that? We have theta 1 and then theta 2. This is for the right-handed medium. Next. Now, if we go to the left-handed medium, it is like this. So this was first demonstrated by Victor Vassilevov. You can see both the figures. The bend of the stick inside the liquid is towards right in the right-handed liquid and towards left in the left-handed liquid in this manner. This liquid, it can be water 1.33, or the second one is actually a thought experiment. So, but in the thought experiment, you can see it bends towards the left. So, there is a negative refraction. This we call a negative refraction angle or negative refraction. This is the magic of LHM. Next. Now, see the simulation. The top one, you can see the top left one. The energy is propagating in the forward direction. The white box actually is the block of the DNG material. So in that block, you can see energy is propagating in the forward direction, that is from left to right, whereas phase is propagating in the backward direction, that is from right to left. The same thing happens in the case of refraction, which is the bottom figure. And if you look at an antenna, which is on the right hand side that we simulated in our laboratory, so from the antenna, it is propagating, energy is propagating outward, whereas phase is coming towards the antenna. That you can see antenna is inside the DNG medium. And because of that, it is the radiation from the antenna is converging when it is connected to a the right-handed material. Next. Now, based on these, Vesselego made some conclusions. The propagation constant beta is real and negative if mu and epsilon are negative. Propagation mode exists that we have seen now. Anti-parallel group and phase velocities, which means they are in opposite direction, group velocity and phase velocity. Because of that, backward propagation occurs. So it follows left-handed rule, and Vp into Vg is not equal to 0. This was one important conclusion. Then we have negative refraction or negative index of refraction. Because n is equal to c by Vp, Vp is negative, therefore n has to be negative. So n has to be negative. These were the important conclusions that he made. Then he found out some consequences also. The consequences are next. If these are negative, then the Doppler effect is reversed, which means if you have a material, metamaterial, and it is approaching you from a distance, then the frequency will not increase, it will decrease, which means you will feel that the material is going away from you. Although it is approaching you, you will feel it is going away from you. Similarly, Gauss-Jensen effect is reversed. This is from the optics, total internal reflection. Babilovo-Cherenkov radiation is reversed. Then Snell's law reversal that we saw. Lensing effect also reversed, which means a concave lens is acting like a converging lens, whereas a convex lens is acting like a diverging lens. Then a flat slab can act like a lens. So flat lens is possible. Superlensing is possible. When you use a lens, usually the K vector has two components, the perpendicular component and the parallel component. Parallel is parallel to the plane of lens. Perpendicular is the perpendicular to the plane of lens. Usually the parallel component is lost because it is parallel, it is not coming. It gets attenuated. But in DNG material, that is also reinforced. So that type of lensing is called superlensing. Then cloaking, which means making an object invisible. This is another simulation that we have made in our laboratory earlier. So you have an antenna in the right-handed medium. When it comes to the left-handed medium interface, it will bend to negatively. So it will bend negatively, therefore it will meet within the left-handed medium. It will focus there. Then it will come out when to the right-handed medium. It will again bend. Therefore, it will again focus on the right-hand side, outside. So one source will have two images, one within the LHM, one outside the LHM. That we have done using a antenna simulation. So antenna is in the RHM medium, which is the source. Now you can see that it is converging to the LHM medium. The output or the wave is converging in the LHM medium. That convergence you can see. Then when it comes to the RHM medium, from the LHM medium, again it is converging. So that we can see from the simulation. Now based on this, we compare the uh, electromagnetic band gap mediums or the photonic band gap mediums with metamaterials, or we classify the materials based on unit cell size versus the lambda. So if A by lambda, A is the cell size, unit cell size. If A is much less than lambda, very small, then Maxwell's equations, they describe the effective medium. Basically, use the Maxwell's equation. But if A is of the order of lambda, like electromagnetic band gap antennas or structures, there the structure is dominating. The structure dominates the property. Interference and diffraction, they will determine the properties of the medium. Whereas if the cell size is much greater than lambda, then geometrical optics that will describe the medium properties like reflection, refraction, shadows, etc. So this is a broad classification of the size, cell size versus the lambda wavelength. Next. Now we discuss this. Now how we are going to realize this? That is more important. Now, we have two things here. One is negative permittivity, other is negative permeability. Since we are conversant with permittivity or dispersive permittivity, like in plasma, ionosphere, if you are conversant with ionosphere, you have seen plasma in which we have a term like 1 minus fp square by f square. So there it is bearing in the form of f square. So let us consider that first. So we'll consider epsilon first, or permittivity first. We'll start with artificial electric plasma instead of a natural plasma like ionosphere. We'll consider artificial electric plasma. How to realize artificial electric plasma? Take uh, conducting rods, very thin conducting rods, and arrange them periodically to form a crystal of conducting rods. So in three-dimensional arrangement is like this, that you see the radius of the rod is r, diameter is 2r, and separation between two rods is a, which means the cell size is a. And we are saying that electric field is along the rod, so you incident an electric field towards this arrangement, so k is towards the rods, so k is in the xy plane, e is in the along the z axis. So consider this. Now let us consider this and do the mathematics next. Now to do the algebra, we take a cell size of A. At the center of the cell size, we take, so that cell size is free space, because between two rods there is free space. So that a cell size is free space. At the center of the cell, we take a metallic rod of diameter 2r. Then for the rod, and the fill factor F1 is defined as the area of the rod divided by area of the cell size. So that is pi r square by a square. For the cell, then F2 is equal to 1 minus F1. So fill factor for the cell is 1 minus F1. Total fill factor sum is always 1. Next. Then since E is in the z direction, therefore you will find the permittivity to be different in the z direction and in the xy direction because of the structure. Structure is like a crystal. Crystals, they show. They do not show a isotropic permittivity, they show anisotropic permittivity. Therefore, in the xy plane, the permittivity will be different, epsilon xy, the xy plane, and that is not of very much significant. They will be very, their contribution will be very less. So we can always neglect them. What is important is epsilon j. So let us find out what will be the expression for epsilon j. Next. This arrangement actually is acting like a plasma fluid. Since we are considering it as a plasma fluid, it will be consisting of equivalent electrons. So its effective electron density, N effective, will be N into fill factor. So fill factor is pi r square by a square. Now electrons here are confined to thin wires, and therefore they act like having a different effective mass. So M effective is mu 0 r square e square n by 2 log natural a by r. Then using Drude model or Lorentz Drude model for the effective permittivity, Ez is, or Ez, which is epsilon effective, that is a function of omega, that is 1 minus plasma frequency effective square divided by omega into omega plus I gamma. And omega square effective is n effective e square by m effective epsilon 0, that is 2 pi c square by a square log natural a by a. Similarly, we can have an optical plasma. This is by Kai and Saleh. So in this, what we do is we take layers of different materials. Here we are taking two materials. One is with permittivity epsilon 1, other is with the permittivity epsilon 2, and there are alternative layers. If we incident electric field which is parallel to the surface of this layer, then in the parallel surface it will see the same permittivity, so it will be epsilon parallel. So whether it is x-axis or y-axis, it will be epsilon parallel. But when the field is penetrating these layers, it is perpendicular or z in the z direction, then it will be epsilon perpendicular. So epsilon permittivity will be tensor in of this form. Now suppose electric field is parallel to this surface. Then E is equal to E1 is equal to E2, but D is equal to F1 D1 plus F2 D2. F1 and F2 are filling factors. So now D you know is epsilon E. So epsilon E is equal to F1, D1 is epsilon 1 E1, D2 is epsilon 2 E2. So put that, then E is equal to E1 is equal to E2, so cancel them. So epsilon parallel is F1 epsilon 1 plus F2 epsilon 2, which is weighted average. But if it is perpendicular, then D is equal to D1 is equal to D2. D for D, we can write epsilon E effective, then is equal to F1 E1 plus F2 E2. Now E effective is D by epsilon effective, and E1 is D1 by epsilon 1, E2 is D2 by epsilon 2. Using that, you can find out epsilon effective is epsilon perpendicular, that is epsilon 1 epsilon 2 by F1 epsilon 2 plus F2 epsilon 1. So we have a weighted harmonic mean for the perpendicular. So this is for optical plasma. Next. So this is about permittivity. Now what about permeability? We know it is difficult to have magnetic effects. Always generating magnetic effects is always difficult. So here we'll do one thing. Let us consider a disk, thin disk, and apply a magnetic field B. The direction is out of plane. If the direction is out of plane, then what will happen? The magnetic field whose direction is out of plane of the disk, that will induce a circular current to oppose this external field B. This is because of the Lenz law. Now, since this is metallic or conductor, the current will be mostly confined to the outer edge, and it will give a magnetic field, but it will be weakly diamagnetic. Mu will be very less than 1. There will be effect, but it will be a small effect, less than 1. Now, since current is on the edge, therefore, instead of taking the whole disk, we can take a ring. So the edge current in the disk will be same as the ring response, or to the same with disk. But here the induction is non-resonant. In both the cases, induction is non-resonant. Therefore, we have weak magnetic field. Now, what to make it resonant? What we will do is we'll cut a portion of the ring. So, if we cut a portion of the ring, there is a current in the ring. Therefore, on both sides of the cut, we will have charge accumulation of opposite signs. So on the top side, let us say we have positive charge. On the bottom side, we have negative charge. So top and bottom, they are separated by a small distance, so that will form like a capacitor. So we have a capacitance, we have an inductance because of the circulating current. So the split is introducing capacitance, metal is giving us inductance. Therefore, we have a LC resonator, so we have got resonance. So resonance response we have got. And omega 0, the resonant frequency will be 1 by root over of LC. Now consider the same split ring. What else is there? Because we have positive and negative charges separated by a small distance, small split. that is giving like a or acting like a dipole antenna. So it will act like a dipole antenna. Because it acts like a dipole antenna, the dipole antenna itself is going to dominate the magnetic response. So the magnetic response that we have got, that is dominated by the dipole antenna. That is to be taken care of. So what we will do is we will introduce another ring which is in the opposite direction to this ring. So it has a short in the opposite direction, parallel to this ring. So dipoles on the two rings are opposite and their effect will cancel each other. So and the capacitance now will come from mostly capacitance. The capacitance due to the slits are very small, but because of the ring structure, the capacitance will come from the two rings separated by the gap. So between the two rings, there will be capacitance that will be dominating. Now, this structure will give better magnetic response because dipole effect is gone and we have got better capacitance. So it will give us a better magnetic response ultimately. Next. So we'll have equivalent RLC circuit. For this is shown here. C0 is equal to epsilon A by D. That you know omega 0 will be root over of 1 by L plus R by I omega 0 into C, I omega into C, not omega 0. Now you can ask me from where we are getting this R. R is because of the conductivity of the rings. So this is how you realize that. Then as we arrange the rods in periodic manner, here also we arrange these split rings in periodic manner to get a magnetic plasma. Like there you got electric plasma, here you get magnetic plasma. So now we can get electric plasma, we can get magnetic plasma. And now we have to design the metamaterial or realize the metamaterial. Next. So we have got electric plasma. Next. We have got magnetic plasma. If we combine these two, then we'll get the metamaterial. So we'll have a region. In the electric plasma, we have a region where epsilon is negative. In the magnetic plasma, we have a region where mu is negative. When you combine them, then this epsilon negative and mu negative, they will be intersecting over a region. That region is the region where we get N negative. So this is how you realize metamaterials or negative refractive materials. So, and this design is shown on the right hand side. Here you can see the square rings, or you can take mostly it is circular rings. This design is showing you square ring. The principle is same. Now that is basically based on a bulk material when you design a bulk material. But and there what we are doing is in the field of electronics, in our field, electromagnetics, we call it transformation electromagnetic. We are transforming the properties of the material. So transformation electromagnetic. From that, we see that the physics behind it is beautiful. But the technology available to realize them is difficult. Therefore, there is less penetration because of the fabrication complexity into the technology domain. Unlike conventional uh, TREM, spatial confinement is not the principle in wavefront technology. If you want to manipulate the wavefront, as instead of the wave itself, we start manipulating the wavefront. Instead of using a material bulk material, then the spatial confinement within the bulk is not the principle. So we do not confine within a spatial region. Refractive index is not useful quantity. So local phase and amplitude control along the surface can be realized. Now let us see how we can do that. Suppose we have a slab like this, a wedge-shaped slab. So where the wedge width is high and where the wedge width is small. What is the difference between these two? If you incident a wave plane wave onto this wedge where it is thick, there the wave phase front will be slowed down. It will move slowly because it has to cover a larger distance, and within a dielectric the speed is lower, and at the end where it is thinner, there the phase will move faster compared to the portion where it is thinner. This is the technology that this is the technique that we are going to use. Now using this technique, what will happen next? If you use this technique, take a slab, incident a plane wave. At the thick portion, it comes out later. At the thin portion, it comes out earlier. Therefore, ultimately, the wave front that is coming out of this slab is bent towards the thin portion. So, this is the principle or the technique that we are going to use. Next. Now, let me ask you a question. Put a question, not ask you, put a question before you. If we could have a spatial distribution of different phase discontinuities along the entire interface of two different medias, what is going to happen? So there is the interface between two media will have different phases along the interface. What is going to happen there? To answer that, let me give you a hint. Next. So the hint is the wave propagation will occur with phase discontinuities. Wherever there are different phases or there are different discontinuities, in the wave also we will get the discontinuities like the following. You can see this. On the left hand side, the uh, vertical line gives you the two phases that there is a discontinuity. On the left hand side, if we have a sine omega t kxx, x is the direction of propagation. On the right hand side, we have a kxx plus phi jump. Phi is the wave discontinuity. So phase discontinuity jump. So that jump is there. So this will happen. Now what will be the effect of that? The effect is the wavefront, is from Huygens principle. This gives you the envelope of a secondary waves with radius or radii Rx is equal to lambda by 2 pi. Phi x, phi is the wave. Now you can see on the left hand side, we have plane wave. Then the interface, in the interface phase is uniform. So when it comes out from the interface, it is plane wave. So it comes a normal incident, it comes out normal incident. On the right hand side on the interface, we have different uh, phases, phase changes along the interface, and because of the change in phase, the radius of the secondary wavefront is of the form lambda by 2 pi phi x. It depends on the phi, therefore it will be different radius. Because of the different radius, the output wavefront is different. It is no more plane, it is different. um, that how to connect the wave fronts. If you connect the wave fronts, you will get this zigzag type of controlled or contoured wave fronts which is coming out at the interface. This principle we are going to use in the meta surface that we are considering now. Next. Now, what is the principle behind it? The principle is Snell's law or discrete law. Now, what is Snell's law from the school? We know Snell's law, sine theta r minus sine theta is 0, n nt sine theta t minus ni sine theta I is equal to 0. And this is the first law. Second law is incident, reflected, and transmitted rays and normal to the interface lie in the same plane. This is what is Snell's law. Why this happens? From how you get this laws? Next. These are based on the principle of least action. From the principle of least action, we apply this, that the momentum and difference between uh, the two paths. Next, the two paths from A to B, we have a red path, we have a blue path, the red path and blue path, the momentum difference is zero. That is the conservation of momentum. Momentum is to be conserved. If momentum is conserved, then you get these two laws. The derivation of these two laws are coming from the conservation of momentum. Next. Now, the Snell's law, nowadays it has been generalized to the generalized Snell's law. Left hand side shows you the Snell's law into sine theta t is equal to n1 sine theta I. Generally, if the interface is having uniform phase. On the right hand side, we see that the interface is having a phase gradient. If there is a phase gradient on the interface, then what will happen? Because of the conservation of momentum at the interface, there is a discontinuity in the phase. So to hold the conservation of momentum, n2 sin theta t minus n1 sin theta I has to be proportional to this phase change, delta phi. So now delta phi, left hand side, you can see left hand side is unitless. Delta phi means dou phi by dou x if it is along the x direction, dou phi by dou x. That is not unitless. So to make that unitless, what quantity is to be multiplied? K 0 inverse. K is the wave number, so K 0 inverse. So if you multiply that, that will be unitless. Right hand side will be unitless. So that way you get the generalized sense. Now, how to realize this gradient in phase? To realize this, we use sub-wavelength resonators on the surface with suitably designed geometry, so that it will scatter electromagnetic waves with the desired phase distribution. So this you will achieve a broad range of 0 to 2 pi phase shift at the interface. We will use deep sub-wavelength thickness on the interface. Separation between these resonators will be sub-wavelength, and they must give you high and uniform scattering amplitude. From each of these uniform resonators, we have to get high and uniform scattering amplitude. That is the technique. Now let us see this figure. You remember the left-hand figure. Now how to realize this? Look at the right-hand figure. Right-hand top figure. In the right-hand top figure, we are using an antenna. This yellow part is the antenna. It is a sub-wavelength antenna. It has a resonating frequency. You can see it has a resonating frequency, resonating peak. That is the resonating frequency. So its amplitude profile that gives you dash line gives you amplitude profile. Solid line also gives you phase profile. Now, if I change the size of this antenna, then the phase profile at the I will get different phases and different amplitudes. Now, how much phase I require, it depends on my application. Suppose I require a phase of 8 pi. So phase change should be from 0 to 8 pi. How to realize 0 to 8 pi? What we do is usually in the 80s and 90s, people used to do something called blazing tiles. So what you will do is you get 0 to 2 pi phase profile. 2 pi is same as 0. So 0 to 2 pi, that this slant line gives you from 0 to 2 pi. Then you have a discontinuity, so 2 pi to 0 come back to 0. Then from 0 to 2 pi, instead of saying 0 to 2 pi, you say that it is from 2 pi to 4 pi. Then 4 pi to 6 pi, 6 pi to 8 pi. Same structure you repeat it. It is called blazed tiles. Using this, you can get the phase profile of 0 to 8 pi. So how the amount of phase profile that you require, you can use this. Now these black dots on this phase profile, they actually show you, here they are indicative of the points where we are putting these antennas, the plasmonic antennas, to give us this response that we have seen in the above. So corresponding to different phases, the black dots Each dot corresponds to a different phase. So how to distribute the phase along this, that is given by these black dots. Next. Now in this structure you can see the phase varies from pi to about 0.2 pi. So approximately the phase variation is from 0 to pi, not 0 to 2 pi that I showed you in the previous slide. It is from 0 to pi, but you require it from 0 to 2 pi. How to get that from 0 to 2 pi instead of 0 to pi? How to get it from 0 to 2 pi? A group led by Capasso in 2011, they realized that from 0 to 2 pi. Next. So instead of using this antenna, they used a V antenna. Now let me tell you what is happening here. Now here you see I am using an antenna of length 2L. If it is of length 2L, on the right hand side I have the positive charge. On the left hand side we have the negative charge. So current is from right hand side towards left hand side. One complete direction, 2L direction is equivalent to lambda effective. So lambda effective is equal to 2L. That is the resonant. Resonant frequency is lambda effective. Effective resonant frequency will be equal to 2L. Now if I take the same one, uh, that is, uh, we can have two currents. So on both the ends we have negative, at the center we have positive. So 2L is the total length, but we have from positive towards left side one direction, positive towards right side one direction. So each one is L, so lambda effective is L. So this is the top one is the fundamental frequency, this one is the first harmonic frequency. So one same length of 2L, we can use it to generate two frequencies, two different frequencies. It can resonate at two different frequencies, fundamental and fast harmonic. That we have to use. Both the frequencies, if we use, then we can get whatever we require. So the second one from the center, if we uh, hold it, we will get a V-shaped antenna. Of each side is A. Now that was the trick. So we have metallic antennas. You can see on the right hand side we are showing metallic antenna. In the first part, the blue part, we have lambda 0 by 2 is equal to L. On the second part, lambda 0 by 2 is equal to 2L. So the second part corresponds to the top antenna that we have shown on the left hand side, and the first part corresponds to the bottom antenna that we have seen on the left hand side. So lambda 0 by 2 is L, or lambda 0 by 2 is 2L, that corresponds to two frequencies. Next. So accordingly the electric field distribution will be this. The derivation we will neglect, we don't require that. And the resonance that you can see, it has the scattering intensity is almost 1. At the required wavelength, the scattering frequency is 1, and the phase variation is pi for each one. For L it is pi, for 2L it is pi, so total is 2 pi. Next. So this antenna has a broader resonance and greater phase coverage. Pi for the first one, pi for the second one, so total is 2 pi instead of a linear one. Now what is the problem here? Because you have a V antenna, this V has on the, if you are in the first harmonic case, in the fundamental case, so at the two ends we will have plus and minus. So because in the V, one end has plus, other end has minus, there will be some, this will be equivalent to a split ring with a larger split, but there will be some magnetic effect that cannot be neglected, or some magnetic effect which can be neglected, because the separation is very large, so you can always neglect the magnetic. Next. Now, these B-shaped antennas, we call it to be symmetric mode or anti-symmetric mode or asymmetric mode. In the symmetric mode, on both these arms, the electric field will be in the same direction. Asymmetric mode, in both these arms, the electric field will be in the opposite direction. So on the bottom arm, if it is from the top to bottom, then in the other arm it will be from the top bottom to top. Now, suppose we have our original incident angle. Incident angle is vertical. So it will be uh, combination of two components, the asymmetric component and the symmetric component that you can see. The red component, which is asymmetric component, and S component, which is the symmetric component. Those parts will be there. So that in that case, the output electric field output is equal to AS exponential J phi S plus AA exponential J phi A. AS is for symmetric amplitude, AA is for asymmetric amplitude. Similarly, phi is for phase. Its mirror reflection, which is the bottom one, that gives you the mirror structure. The bottom one is the middle one. In the middle one, it is mirror reflection. Since it is mirror reflection, what you will get is the phase reversal. Mirror reflection is 180-degree phase reversal. So E out will be exponential J phi s plus pi. Similarly, exponential uh, J phi a plus pi. So if we arrange these two in a proper manner, like the one shown in the bottom, so you start with a simple antenna, stick antenna, then a V antenna, then another V antenna, then another V antenna, then the mirror reflection of this structure. So the parts the dipole antenna is 0, then pi by 4 depending on the angle, pi by 4, then the next is 2 pi by 4 is negative depending on the second angle, 3 pi by 4, then 4 pi by 4. So take its mirror reflection next one. So 4 pi by 4 after that, 5 pi by 4, 6 pi by 4, 7 pi by 4. So you have covered 0 to 2 pi distance, and the size and the angle they are chosen to get uniform amplitude and 2 pi coverage. This was by Capassos group. This is NU. They published in 2011. Next. Now this shows you the arrangement. You can see along the X direction we have all those yellows are those V antennas, and along the Y direction what is realized is in the right hand side. Along the Y direction you can see there is no change in the shape. So since there is no change in the shape, each shape corresponds to a particular phase. There is no change in the shape, so there is no change in the phase. So along the y direction, no change in the phase. So d phi by dy is equal to 0. Whereas along the x direction, there is change in phase. So d phi by dx is not equal to 0. That is the phase gradient. We are getting a phase of 2 pi over a length of gamma over a period of gamma. Therefore, phase gradient is 2 pi by gamma. So d phi by dx is equal to 2 pi by gamma. Depending on what will be your required phase, you will design the antenna based on this. Next. Now, suppose you want to put more antennas or have a larger gradient. You want to have a why you will have a larger gradient? Because you want to have a larger negative angle or larger angle. You want to change the angle. So depending on what is your angle, you will require a phase gradient. If the phase gradient is more, which means within the small uh, period you want to put your antennas. Antennas have finite size. Therefore, you cannot have all the antennas, many antennas within a small size. More gradient means within small size you want to put more antennas. That is not possible because of the finite size of the antennas. They will overlap. You have to avoid that. If you have to avoid that, which means you cannot put all the antennas. You may be having two antennas or three antennas for a larger gradient. In that case, what will happen? There will be less efficiency. Efficiency trade-off is to be done. What is meant by efficiency? Ideally, we should have a continuous phase gradient, which means we should have antennas distributed continuously at every point along the interface. But practically that is not possible. Antennas have size, therefore there has to be separation between size. Once you reduce the if you reduce the length gamma, the size will be reduced. So antenna size, if you reduce this gamma, then antenna number of antennas is to be reduced. Number of antennas is reduced means you will not get the proper phase distribution. So efficiency trade-off is to be there. How much phase distribution you want. Depending on that, you have to do this. Next. This shows you, this figure shows you if you distribute it like the one that we showed, what you are going to get. The black one on the left hand side, it is angle of refraction versus angle of incidence. On the left hand side, you can see the black one, there is no phase gradient. And this is for refraction. Whereas for the red one, you can see the refraction angle is negative. Possible negative refraction angle is there corresponding to positive incidence, and that is there. So negative refraction is there. Similarly, on angle of reflection, you can also see that the angle of reflection is equal to angle of incidence. So black line is straight line of 45-degree phase, whereas red is anomalous reflection. It is not following this theta I is equal to theta r. So that happens in case of this V-shaped antenna distributed surface. Next. Now finally the question is why we choose metasurface. Uh, Three types of materials we will consider: metamaterials, metasurface, and frequency selective surface. Metamaterials, you have extra field control. Metasurface also you have that. Metamaterials, you have signal processing ability. Metasurface also you have extensive signal processing ability. FSS, the processing is for filtering and polarization. Then metamaterials are bulky. Metasurface have reduced dimensionality. FSS have reduced dimensionality. These are two-dimensional structures. And then they have small profiles 2D. Then high loss in metamaterials, metasurface have low loss, limited signal processing in FSS, and then fabrication difficulty in metamaterial because as you go to higher frequency, the roughness of the materials on which you are designing, substrate surface roughness, that comes into play. And you have to have layered structure. So that creates problem in metamaterial fabrication. Here it is comparatively easier in metasurface. It is easier. FSS, the uniformity, there has to be some restriction. So therefore, metasurface is the choice today. Next. Now after this, we will see some of the applications for the next 10 to 15 minutes. I will go as fast as possible because we were delayed by 10 minutes. I will take 10 minutes more if Professor Vera permits. So some of the applications that we did in our laboratory are based on this. We realized a planar lens by simulation. We started with using a simulation. The purpose was to reduce the thickness of the lens Lens is usually of the order of lambda. Thickness of the lens is of the order of lambda. That we try to reduce by engineering the secondary wavelets that we have just discussed. Next. Then let us see the what are the reflections, laws of reflection. We are going to use the phase, change in phase. So reflection phase, they shift at if you have a dielectric to dielectric interface, the phase shift is 0 or pi. If you have a next dielectric to piece interface, the phase shift is always pi. And if you have next, if you have lossy materials to interface of a lossy material, then the phase shift can be anything between 0 and 2 pi. So this we know, the reflection principle. So you are going to use that principle here now. So here we see uh, what we simulated and realized in our laboratory, the meta elements, which instead of using a V-shaped antenna, actually why you used V-shaped antenna? Because it is a plasmonic antenna, it is a sub-wavelength antenna, small antenna, and it is regenerative. So any antenna we can use instead of a V-shaped antenna. We tried using this square antenna that you see on the left-hand side, then the cross antenna, and then the Jerusalem cross antenna. These we designed in the laboratory in our simulation. You can see that the reflection magnitude is between 1 to 0.78. So lowest is 0.78, which is acceptable. More than 0.707 is always acceptable. Reflection phase is between 200 to minus 200. So that much of phase. So 0 to 2 pi, 360 we easily get using the first one. Using the second one also we get same phase and the amplitude is acceptable. Third one also the amplitude is acceptable. So this can be used for elements instead of V antenna. You can use these antennas. That we first we got this idea. Next, then we um, generalized or we developed a or we modified the Jerusalem cross. You can see the antenna here in the top left. We have four Jerusalem cross. They are connected in such a manner that there is a ring, and on the ring on each arm we have a T like of that. So here you can see the magnitude from that if we do a reflection. So from that reflection magnitude is more than 0.98. Always from 1 to 0.98 it is there. And phase is 150 to minus 150. So about 300 degree that we get. So reflection phase and reflection magnitude that we can see on the right hand side at different frequencies. Next. Uh, then what we did is we arranged these rings or the Jerusalem cross, modified Jerusalem cross in this manner. We found out what is going to give us plus pi, what size is going to give us minus pi. And from plus pi to minus pi, we arranged in this manner. So from plus pi to minus pi, then from plus pi to minus pi. If we arrange in this manner, so pi to minus pi, the wave is moving from the pi direction to the minus pi direction in two frequencies following this principle sine theta r minus sine theta I is lambda 0 by 2 pi ni into d phi by dx. That generational slope following that. The wave is tilted using this. We have first we saw that we can tilt the wave front, the transmitting wave or the reflected wave is getting tilted. That we saw first. Next, used that principle to the realize the flat lens. This also we did in our laboratory. So you can see how the phase is distributed. 180 degree to minus 180 degree is on the left hand side. On the right hand side, it is minus 180 degree to 180 degree. So if you look at this simulation on the right hand side, on the simulation you can see on the left side is 180, it goes to minus 180. So the tilt is towards minus 180, from 180 towards minus 180. Similarly, from the right as you can see 180 to minus 180. Therefore, that way the phase is or the wave is converging. It acts like a converging lens. So, flat surface that we saw in the previous slide is acting like a converging lens here that we saw. So that we realize next. Next. In the X-band, how we design different surface atoms. This is for linear polarization. Next. This is for elliptical polarization. Next. This is for circular polarization. So three atoms we design. Next. Next. This gives you, this is for your reference only. This is available in the handout that will be provided by Professor Behra. So I am not going to discuss this. Next. This is the phase control over the surface. What we do is we found out what is the phase gradient. This we found out to be 43 degree using this formula. Then we found out how many unit cells will require. We total require is 360-degree phase change. So 360 degree by 43 is approximately 8. So we require 8 unit cells to realize 360-degree phase difference. Next. So the phase control using those three, the for circular, linear, and elliptical, that is shown here for different types of surface atoms. You can see the amplitude is always above zero point 0.7. It is almost zero point 0.9, 0.99 like that. And phase we are getting about 300 to 360, between 300 to 360. Next. Now let us consider applications. This was using the metamaterial. You can see the first one is we are incidenting electric field on a plane plate, normal metallic plate, plain plate, and its a reflection you can see on the top left. Then the bottom is in the ground plane. We introduced a bomb, metallic bomb, so there is scattering. If you incident it on the bomb, there will be scattering. On the third, on the right hand side, what we have done is we have covered the bomb with layers of metamaterial. So that we call a metamaterial carpet. Now, if you insert that electromagnetic field onto this carpet, onto the bomb which is covered by the carpet, now you can see the reflection. The reflection of this one and the top one, these are similar. The scattering is gone. So the bomb is clogged or becomes invisible. So this is a carpet clock. Instead of using this bulky material, next, how we used meta surface that is shown on the right hand side, and you can see this that we are getting the same reflection like on the left hand side. If you look at the uh, left, complete left, this is the reflection from the metal surface, and complete right is the reflection from the clocked bomb, and middle one is the reflection from the bomb. So now you can see that right hand side and left hand side are almost similar. Middle one is giving you this category. So clock we can use meta surface next. Then we wanted to realize a high gain antenna. What you do to realize a high gain antenna, usually you take a parabolic reflector, and at the focus of the parabolic reflector you put your gain. Here what we did is instead of a parabolic reflector, we used a metasurface, and which is equivalent to the parabolic reflector. What happens in the parabolic reflector at different points of the parabolic surface, the phase or the path is different. So because path is different, so phase is different. So you calculated the phase, put the according to what should be the phase at different points. Those phases we arranged on the planar meta surface. Below that is shown the arrangement of phase, and of phase what we did is we quantized the phase between 180 to minus 180. We quantized the phase in the manner like 00, 0001, that way up to 111. Each quantization phase was realized using a different size of the meta atom, and the bottom one, left bottom one, shows the amplitude. So from that the phase distribution is at the top view of the surface, that we realized it at the B. Reflection coefficient comparison between the feed of microscope MSA is shown at the C. Next. So this is the realized one, fabricated one, and you can see the gain. On the middle one, the gain right hand side is the experimental arrangement. So what we did is linearly polarized quasi-spherical incident from a microscope antenna. That is the top one. In the bottom figure, the top is that bottom is radial progressive phase reflective metasurface. From that, because it is a reflective metasurface and it is converging, acting like a converging lens. So the beams are converging. Because they are converging, the gain is higher. Next. Then we use the same principle to realize a high gain CP cavity antenna. What we did is the same structure we took, and above that structure we put a linear to circular polarizers meta screen, LP to CP meta screen, that we put on the top. Because it is a linear to circular polarizer meta screen, so the reflected beam from the bottom, which is linearly polarized, when it passes through that polarly polarized transmission through that screen. And the design of the screen is shown on the right hand side in the middle. And the right hand side shows you what is the axial ratio. Axial ratio is 3 from 9 to 11 gigahertz. So it is below 3, well below 3, between 9 to 11 gigahertz. You can see from 9.5 to about 10.5, we get very good axial ratio. In this case, high gain and a good axial ratio. Gain is above 7 and axial ratio is below 3. So that we realize it is published. Earlier papers were also published. This is also a published paper. Next. This shows you the realized, the fabricated antenna here in the same one. High gain CP cavity antenna is shown here. Uh, what we realized. So here A is the source microstrip antenna, B is the bottom reflective surface, metasurface, C is the top polarization converter metasurface. So there are two metasurfaces, one microstrip antenna. Uh, Using that, we realized this. Next. Then what we did is using one antenna, one microstrip antenna, we realized four beams. So this is called a quad beam antenna. So four main beams we realized. So this that um, the top left shows the surface, complete surface. You can divide it into four equal parts. One part is shown here on the figure B. The phase distribution of that part, its reflection is the top left one. Then of this, those two take the reflection on the bottom side. So that will give, each one will give you a beam. So left one, first one will give a beam like this going towards one corner. The other one is, since it is reflection, so it will be going to the different second corner. Their reflection is to the bottom, so those beams will go into the bottom two corners. So this is the principle of using a quad beam antenna. Next. Once we realized the quad beam antenna, then on the quad beam antenna, what we did is we put a reflecting surface. We put the LP2CP polarizer. So we got quad beam, circularly polarized quad beam radiation also. So that is also published. So this was the second principle. Next. Now, where to use this to see the use? We used the CAD of a MiG-21 fighter, and there we used a pentabeam surface. On the MiG-21 fighter, what is the problem? On the tail antenna, the beam gets interrupted by the antennas of front side, by the plane front side, also by the wings. So to avoid that, what we did is we put the pentabeam antenna on the MiG. So they were not directly to the body of the aeroplane. Therefore, you are getting the continuous communication using this. Next. Then I think Bhatti says what happens here is, let me tell you what happens here, is the propagation direction along the propagation direction K, the beam is rotating. The beam that you are generating is rotating along this with a phase singularity at the center of the propagating beam. So you are getting like a helix. It has donut shaped intensity, cross Q shaped wavefront like a helix that you can see here. And this can impart orbital angular momentum and it can encode optical information. Next. This is the simulation that we did in our laboratory. Next, I just want to show you how we realize this. So this shows you two proposals of phase distribution and their realization in the laboratory and the fabrication. And after the fabrication, you can see on the right hand side bottom, it is simulated field result. So you can see at the center, along the center, there is no beam. The beam is propagating along the center direction, but it is rotating around the direction of propagation. At the center, you have what we call the singularity. That you can see on the phase singularity. You can see just adjacent to that one. A, B, C. These three are shown here. The far field phase pattern for the microstrip antenna when we have mode 1 and when we have mode 2. So the model 1, model 2, those two models are shown here. Next. This shows you how it is generated. There different modes, different models at different frequencies. And now what is the advantage here? Because of different models or different modes, we generate two modes. Two modes means it is corresponding to two orbital angular momentum, two quantized orbital angular momentum. Each mode is of a definite value of orbital angular momentum. And these are quantized and they are orthogonal. So in each mode, using one antenna, you can generate up to n modes. In each mode, you can send information, different information. So with one antenna, we can send many information because these modes are orthogonal to each other. So that is the major advantage of generating the OAM vertex. And its use on aeroplane tail or a car is shown here. These are from CAD models. Next. Then we used this principle to reduce RCS. What we did is we generated different phases, arbitrary phases. Instead of arranging the phase or generating the phase in a structured manner, you generate it in the random manner. If we generate it in the random manner, then there will be reduction in RCS. The amount of reduction is shown on the right hand side. The left hand side, top left hand side, shows the fabricated prototype of the beta surface and how much reduction is done is shown on the bottom right hand side. Minimum reduction is 8 deviation and maximum we got up to 20 deviation at different frequencies. Next. This shows what happens, how to reduce this this RCS. The right hand side brown is the reflection for different frequencies 9.5, 10, and 10.5 from a metallic surface, normal copper plate. And when the plate is replaced by metasurface with random distributions, how the change has occurred 9.5, 10, and 10.5. So on the left, right hand side, you have solid reflection. On the left hand side, you have scattered reflection because it has scattered, the solid has become scattered, the RCS is reduced. Next. This shows the simulation of the same one. The top left is from the metal, the top bottom is from the surface, right hand side is also from the surface. The scattering is clearly visible there. Metal, it is going back in the and whereas here it is going in different directions. For the metal surface, it is scattering in different directions. Next. This shows a supercell configuration. I think that I'll skip now. Next. This shows the if you have supercell configuration, the RCS will be further reduced. Using 3 × 3 supercell configuration, we have reduced the RCS. This we have done in our laboratory. Next. This is an application. With this, I will end. What we did here is for the cognitive radio, we designed an antenna. In the antenna, the bottom, you can see we have a slot antenna. So we have a feed line, then a slot antenna. Above the slot antenna, we have PRS. PRS is partially reflecting surface. So on this partially reflecting surface above the PRS, we give another partially reflecting surface. Above that, we gave the polarization converter. So accordingly, we generated circularly high gain, circularly polarized antenna system for cognitive radio application. Advantage is we use the slot antenna, so it is broadband, bandwidth is large, which is required for cognitive radio, and we used cavities here to uh, increase the gain. Every period cavities, these cavities that you see, the bottom cavity, then the middle cavity, these are two Fabry period cavities. So because of two Fabry period cavities, how we have enlarged the bandwidth. If you have two regenators, that ultimately two regenators are regenerating at different frequencies, and the frequencies are close to each other, then the bandwidth, the total bandwidth of the system increases. So that principle we have used here, and we have increased this cavity length. You can see next. So you can see that the axial ratio is around 3, between 13 to 13.75 to 14.5. Axial ratio is around 3. Next. Next. I appreciate your patience. You stayed with me. Oh, thank you. If you have any comments or questions, I'll be happy to answer them.
Thank you, sir. With all due respect, I would like to say that it was very much in detailed presentations that you have presented here, and hell lot of work you have done. And we have heard from our guide, Professor Bera sir, about your contribution in shaping the antenna and RF engineering group future. And so now it is the question and answer session. I would like to say that any doubts if you have, the online participants and the offline, so you can ask now. We will have a very short session.
They can ask now, and if time does not permit, they can contact me later also. They can get my address from Professor Vera, my email. Thank you.
From the online audience, can we have one or two questions? Actually, you don't realize that how grateful you are now, uh, to be able to communicate directly here with sir. And we all from our team of short-term course, we're very much grateful that sir has took his precious time for us, and he is here with us. Okay, then if you don't have any questions, we are going to wind it up. And I would like to request our guide, Professor Behra sir, to extend the vote of thanks. Sir, please. Sir, sir. Video on, please. Awesome.
Sir, really we are honored or privileged to find you as our speaker today. So you have already covered the basics of metamaterial and metasurfaces, which will help you to our participants in future, although not now. Uh, those who are working in future, working in this area, it will be helpful for them in future. Sir, before saying something, we are having a token of appreciation for you. This is for you. Please accept virtually. Then I'll send it to you um, later on.
Thank you.
Thank you, sir. So, thank you, sir. This is only your inspiration. We have started in 2015, the first edition of this short-term course. So you might have remembered. You have attended all three, four, I think, last four editions you have attended before COVID.
Yes, yes.
In
Before
19
COVID, I
also,
have attended
yes,
everything.
sir. I think 19 also you are present. I think so. 19 or
19,
no, 17
no,
I mean.
17 I
19,
was there.
I think
19 I
7.
had accident.
Okay, sir.
19 I had accident.
Yes, yes, yes. That incident happened in 1990. So up to 17 you attended all the short-term courses 15, 16, 17
Great.
continuously 3 and virtually this is
Fourth.
in 2023. This is the fifth edition, sir.
Yes. I am attending the fourth one. For me, it is fourth.
Yes, this is fourth one. So thank you, sir. If our participant have some questions, they will contact me. I will forward to you. Later on, they may contact you.
Yes.
So thank
My
you
best
once again.
wishes. My best wishes for a successful workshop. Thank you for
Thank you,
having
sir.
me.
Namaskar.
Yes.
Thank you, sir. Thank you, sir. So here we are.